So ground-based methods and ground-based measures are integral for calibrating and validating remote sensing data sets from airborne and spaceborne scales. There exist a large number of ground-based methods for deriving leaf area index and counter metrics, and it is found that some of them are suited to certain environments, and different methods don't necessarily match up with each other. So this gives rise to investigation or into comparison of different indirect measures for sensing leaf area and canopy cover metrics from the ground. So what is leaf area index? Leaf area index can be defined as half the total leaf area per unit of ground area. And so if you can imagine a forest being squashed down and the leaves being placed side by side with one another, the leaf area index is the number of layers stacked on top of each other. Crown cover can be defined as the proportion of the forest floor covered by the vertical projection of the crown, where tree crowns are treated as opaque. And foliage projected cover is just a variation of crown cover where that includes sensing gaps within the canopy and also only the vegetation separating from the branch and stem components. Leaf area index is an essential climate variable and has been used in water catchment modelling, climate modelling and burn severity assessments, just to name a few. So broadly, ground-based methods for leaf area index can be split up into two different categories, direct and indirect. Direct methods are normally considered as the most accurate methods because you can directly sense and measure the leaves by hand. But these methods are very costly generally and aren't suited to particular environments such as forests. Indirect measures, on the other hand, have been around for quite some time, but they can be done using a variety of instruments, and they allow for a greater area to be sampled more efficiently under the forest. So are these indirect methods that derive the same metric comparable? And that was really the main question that I was looking at answering. It can be found that, well, from the previous research, they found that leaf area measures from different instruments don't always match up, and they're not always biased in a way that you can calibrate the sensors. So this question was the fundamental to this research. So the study area we looked at was the Rushworth Forest in central Victoria. It is approximately 2 hours drive north of Melbourne. It is a box ironbark forest, which is representative of dry climate conditions inland in Victoria. So the instruments selected were the LAI 2200 plant canopy analyzer, which is an established method being used in a number of studies. And we also have hemispherical photography from 2 different instruments. The Nikon D90 was a high resolution camera, and the CR110 is a low resolution hemispherical camera. We also chose to incorporate 2 laser scanners. One was the Trimble CX, which is a phase-based scanner, and the Regal BZ400 is a time-of-flight scanner. So the main difference between them is the time-of-flight scanners can generally sense a lot greater distance, so the range is a lot more effective than phase-based scanners. So what exactly are they measuring? So the LAI 2200 senses light, so you don't get an image, unfortunately, whereas with the cameras you are able to see what you are sensing. And with the laser scanners you can get a 3-dimensional point cloud. So it's really a hemispherical photograph with range. And on the upper right hand side is just a projected 3D point cloud of the forest, coloured by intensity. So how can you derive leaf area index and cover metrics from these instruments? And that is through classifying the sky, or the upward-looking photo, into sky and non-sky. And then this can be analysed by splitting up the sky and non-sky into zenith rings, where the 0 degree zenith angle is straight up and 90 degrees is on the horizon. So using Miller's formula, you can incorporate the proportion of gaps over each ring to derive your leaf area measure. But here I've said PAI, which is planetary index, where unless you distinguish between the foliage components and non-foliage components of your imagery, you'll be deriving plant area instead of leaf area. And plant projective cover can be derived just from using a narrow zenith width, so pretty much the vertical projection of the gap measure straight up. So a number of different sampling designs were incorporated in the study, and one was quite unique, and it was unique because in the literature there is no one established method that's recommended, especially in forest environments, for sensing a robust measure of leaf area. So on the left we have a 40 by 40 metre plot where the sampling intensity or density is more sparse throughout from the middle to the corners. And then on the right hand side we have a modified SLATS transect, where SLAT stands for the Statewide Land Cover and Tree Survey, which was established in Queensland for the assessment of foliage projective cover in these Australian environments. And we modified the SLATS transects, where they are 3 100 metre transects, but we only decided to take a small number of measures which covered a larger area. So the first test we did was we chucked all the instruments at one point and to see and compare the gap probability over the zenith angle. So on the x-axis we have zenith, and on the y-axis we have the gap probability. So we can start to see trends emerging between the instruments for this one point, and this will be investigated further. So this is the comparison between the 2 laser scanners at 2 different points. And ideally, you'd like to see the 2 lines match up across all the zenith angles. But, so what is causing these differences? And one, as I mentioned before, is the effective range of the instruments. So on the right hand side we have a point density graph, where the y-axis is the total proportion of returns, and the x-axis is over the range. So you can see the Trimble instrument, or the phase-based instrument, decreases in effective range a lot quicker than the tungsten flight instrument. But what does this mean in our forest environment? So our trees are roughly 15 to 20 metres tall, and the effective range of the phase-based instrument is equal to about that distance. So therefore, in that range, you would expect to see these 2 gap probabilities over a narrow zenith angle to be the same. So we would expect to see this zenith angle, these gap probabilities here, be similar for a small zenith angle, but they're not. So what happens when we add another instrument? So here we've looked at adding the hemispherical camera, and we can see that the hemispherical camera matches up quite well with the range-based instrument, whereas the phase-based instrument still isn't quite there. So this indicates that a phase-based instrument might not be suited to these foliage conditions. So this was a comparison done at 6 different plots throughout the study site, where the study site was a 3 by 3 kilometre area. And these were just measurements at the centre of each plot. The instruments used here were the Trimble, the phase-based laser scanner, the CR110 and the Nikon D90. So trends are starting to emerge between the 2 imagery or hemispherical instruments, which match up quite nicely, where the high resolution camera is consistently above but matching close with the low resolution camera. And significantly as well, the standard deviations over all points are quite consistent across the zenith angle range. So when we increased our sample size and swapped the LAI 2200 for the terrestrial laser scanner, because it's just not feasible to scan 72 points in a forested environment in a feasible period of time. So this comparison here was the three instruments measured at exactly the same point at the same time, or just after one another, and 72 points were measured. So a consistent trend is really developing between the high resolution camera and the low resolution camera, where the high resolution camera is consistently above, measures a higher gap probability than the low resolution camera, and once again the standard deviations are quite similar. They're also statistically significant. So this indicates there might be potential for calibration between these instruments in this study site, or of a representative forest such as ours. So finally, what all these results are telling us is there is a potential to calibrate these instruments within our study site. But what needs further investigation is what number of samples and the spatial location are required to obtain a robust measure for leaf area index, and these canopy cover metrics for the validation and calibration purposes of the remote sensing datasets. And furthermore, the inclusion of accurate representative clumping, leaf angle distribution, and the proportion of woody and non-woody corrections are required to get a real measure of effective leaf area index rather than your planetary index. So I think I have plenty of acknowledgements, but we might have time for a couple of questions. One question. Any questions? Yes.
So do you think that the face is less like or another type of orthogon? Because you just listed that one.
Yeah. Potentially, but you'd want to be sensing vegetation that's actually quite close to the scanner. So if you're looking at measuring trees that were greater than 20 metres high, then potentially it's not suited to that type of environment. So, yeah. So thanks everyone, and this concludes our session.